early work with Roger Penrose showed that classical general relativity predicted the universe had a beginning in a Big Bang singularity. That the universe had a beginning in the Big Bang 13.7 billion years ago is now accepted by most people working in cosmology, and is supported by the discovery of a faint background of microwaves. The prediction of singularities indicates that classical general relativity breaks down, and has to be replaced by a quantum theory of gravity. Jim Hartle and I proposed that the quantum state of the universe should be defined by a path integral over all compact Euclidean metrics without boundary. In other words, the boundary condition of the universe is that it has no boundary. The no boundary condition implies that the laws of physics hold everywhere, even at the beginning of the universe. Together with Thomas Hertog, Jim and I showed that the no-boundary proposal predicts that the universe began with a period of inflation, a prediction which may be confirmed tomorrow, when the data from the Planck satellite are published. I feel a sense of achievement that I have managed to make these contributions, despite having ALS. I have not allowed my disability to stop me doing most things. My motto is there are no boundaries. So remember to look up at the stars and not down at your feet. Try to make sense of what you see, and wonder about what makes the universe exist. Be curious. And however difficult life may seem, there is always something you can do, and succeed at. It matters that you don't just give up. Hello, can you hear me? I can hear you too. Thank you for being here this evening. Although I would love to be there in person, the idea of being the first person to appear as a hologram on the stage at the Opera House is too good an offer to refuse. When I do other speeches, I'm not able to do this. I must point out that this is not the first time I have been a hologram. I was supposedly represented by a hologram in an early episode of Star Trek, The Next Generation. In the episode, I was playing poker with Isaac Newton, Albert Einstein, and Commander Data. I won. I was unable to cash in my winnings of 140 Federation credits. I approached Paramount Studios, but they didn't know the exchange rate. My performance was outstanding. I was very convincing as myself. Almost as convincing as Eddie Redmayne. It is thought to be the subject of a Hollywood movie. And it has put me in a reflective mood. So I hope you will forgive me for looking back over my life, and how our understanding of the state of the universe has changed. I will also try to look forward beyond the present horizon. I was born on January 8, 1942, exactly 300 years after the death of Galileo. However, I estimate that about 200,000 other babies were also born that day. I don't know whether any of them were later interested in astronomy. I was born in Oxford, even though my parents were living in London. This was because Oxford was a good place to be born during World War II. The Germans had an agreement that they would not bomb Oxford and Cambridge, in return for the British not bombing Heidelberg and Göttingen. It is a pity that this civilized sort of arrangement couldn't have been extended to more cities. We lived in a tall, narrow Victorian house in Highgate, which my parents had bought very cheaply during the war, when everyone thought London was going to be bombed flat. In fact, a V-2 rocket landed a few houses away from ours. I was away with my mother and sister at the time. Unfortunately, my father was not hurt. For years afterwards there was a large bomb site down the road, in which I used to play. At that time, during and just after the war, Highgate was an area in which a number of scientific and academic people lived. In another country they would have been called intellectuals, but the English have never admitted to having any intellectuals. All these parents sent their children to Byron House School, which was a very progressive school for those times. I remember complaining to my parents that they weren't teaching me anything. They didn't believe in what was then the accepted way of drilling things into you. Instead, you were supposed to learn to read without realizing you were being taught. In the end, I did learn to read, but not until the fairly late age of 8. In 1950, my father's place of work moved to the northern edge of London, so my family moved nearby to the cathedral city of St. Albans. I was sent to the high school for girls, which despite its name took boys up to the age of 10, but later I went to St. Albans School. I was never more than about halfway up the class. It was a very bright class. My classwork was very untidy, and my handwriting was the despair of my teachers. But my classmates gave me the nickname Einstein, so presumably they saw signs of something better. When I was 12, one of my friends bet another friend a bag of sweets that I would never come to anything. I don't know if this bet was ever settled, and if so, which way it was decided. I had 6 or 7 close friends, and we used to have long discussions and arguments about everything, from radio-controlled models to religion. One of the things we talked about was the origin of the universe, and whether it required a God to create it, and set it going. I had heard that light from distant galaxies was shifted towards the red end of the spectrum, and this was supposed to indicate that the universe was expanding. but I was sure there must be some other reason for the redshift. Maybe light got tired, and more red, on its way to us. An essentially unchanging and everlasting universe seemed so much more natural. It was only after the discovery of the cosmic microwave background, about 2 years into my PhD research, that I realized I had been wrong. My father was very keen that I should go to Oxford or Cambridge. He himself had gone to University College, Oxford, so he thought I should apply there. But at that time, University College had no fellow in mathematics, so I had little option but to try for a scholarship in natural science. I surprised myself by being successful. In the end, I have wound up being a professor of mathematics, but I have not had any formal instruction in mathematics since I left St. Albans School at the age of 17. I have had to pick up what mathematics I know as I went along. When I used to supervise maths undergraduates, I would keep 1 week ahead of them in the course. At Oxford, the physics course was arranged in a way that made it particularly easy to avoid work. I did 1 exam before I went up, then had 3 years at Oxford, with just the final exams at the end. I once calculated that I did about 1,000 hours work in the 3 years I was there, an average of an hour a day. I'm not proud of this, I'm just describing my attitude at the time, shared by most of my fellow students. Because of my lack of work, I had planned to get through the final exam by doing problems in theoretical physics and avoiding questions that required factual knowledge. But I didn't sleep the night before the exam because of nervous tension, and so I didn't do very well. I was on the borderline between a first and second class degree, and I had to be interviewed by the examiners to determine which I should get. In the interview they asked me about my future plans. I replied that I wanted to do research. If they gave me a first, I would go to Cambridge. If I only got a second, I would stay in Oxford. They gave me a first. I was 20 in October 1962, when I arrived in Cambridge at DAMT, the Department of Applied Mathematics and Theoretical Physics. I had applied to work with Fred Hoyle, the most famous British astronomer of the time. I say astronomer, because cosmology then was hardly recognized as a legitimate field. However, Hoyle had enough students already, so to my great disappointment, I was assigned to Dennis Sharma, of whom I had not heard. But it was just as well I hadn't been a student of Hoyle, because I would have been drawn into defending his steady-state theory, a task which would have been harder than getting across the harbor bridge at peak hour. I hadn't done much mathematics in the very easy physics course at Oxford, so Sharma suggested I work on astrophysics. But having been cheated out of working with Hoyle, I wasn't going to do something boring like Faraday rotation. I had come to Cambridge to do cosmology, and cosmology I was determined to do. At that time, cosmology and gravitation were neglected fields that were ripe for development. So I read old textbooks on general relativity and traveled up to hear relativity lectures at King's College London each week. I followed the words and equations, but I didn't really get a good feel for the subject. At that time, it became clear something was not quite right with me. Already in Oxford, I had noticed that I could no longer row a spelling boat properly. The Christmas after arriving in Cambridge, I went home. It was a very cold winter and my mother persuaded me to go skating on the lake in St. Albans, even though I knew I was not up to it. I fell over and had great difficulty getting up again. My mother realized something was wrong and took me to the doctor. I spent weeks in Bart's hospital and had many tests. They never actually told me what was wrong, but I guessed enough to know it was pretty bad, so I didn't want to ask. In fact, the doctor who diagnosed me washed his hands of me, and I never saw him again. He felt that there was nothing that could be done. In effect, my father became my doctor, and it was to him that I turned for advice. At first I became depressed. I seemed to be getting worse pretty rapidly. There didn't seem any point working on my PhD, because I didn't know if I would live long enough to finish it. But then the condition developed more slowly, and I began to make progress in my work. After my expectations had been reduced to zero, every new day became a bonus, and I began to appreciate everything I did have. While there's life, there is hope. And there was also a young woman called Jane, whom I had met at a party. Getting engaged lifted my spirits, and I realized, if we were going to get married, I had to get a job and finish my PhD. I began to work hard, and I enjoyed it. The big question in cosmology in the early 60s was, did the universe have a beginning? Many scientists were instinctively opposed to the idea, because they felt that a point of creation would be a place where science broke down. One would have to appeal to religion in the hand of God to determine how the universe would start off. Two alternative scenarios were therefore put forward. One was the steady-state theory, in which as the universe always expanded, a new matter was continually created to keep the density constant on average. By the time I began my research, the steady-state theory was already in trouble with observations, but the final nail in the coffin came with the discovery of a faint background of microwave radiation in 1964. The only reasonable interpretation of the background is that it is radiation left over from an early very hot and dense state. As the universe expanded, the radiation would have cooled, until it is just the faint remnant we observe today. But there was a second alternative to a beginning in time, which is a bouncing, or even cyclic, universe. Perhaps the universe had a previous contracting phase, and that it had bounced from contraction to expansion at a high but finite density. This was clearly a fundamental question, and it was just what I needed to complete my PhD thesis. Two Soviet scientists, Lifshitz and Khalatnikov, had claimed to have proved that contraction in general relativity without any special symmetry would always lead to a bounce, with the density remaining finite. This result was very convenient for Marxist materialism, because it avoided awkward questions about the creation of the universe. Lifshitz and Khalatnikov were members of the old school in general relativity. That is, they wrote down a massive system of equations and tried to guess a solution. But it wasn't clear that the solution they found was the most general one. A new approach was introduced by Roger Penrose, which didn't require solving the field equations explicitly, just certain general properties, such as that energy is positive and gravity is attractive. Penrose had showed that once a dying star had contracted to a certain radius, there would inevitably be a singularity, a point where space and time came to an end. I realized that similar arguments could be applied to the expansion of the universe. In this case, I could prove there were singularities where spacetime had a beginning. So Lifshitz and Khalatnikov were wrong. General relativity predicted that the universe should have a beginning. Up to 1970, my main research interest was in the Big Bang singularity of cosmology, rather than the singularities or black holes that Penrose had shown would occur in collapsing stars. My work on black holes began with the Eureka moment, a few days after the birth of my daughter, Lucy. While getting into bed, I realized that I could apply to black holes the causal structure theory I had developed for singularity theorems. In particular, the area of the horizon, the boundary of the black hole, would always increase. When two black holes collide and merge, the area of the final black hole is greater than the sum of the areas of the original holes. This suggested that the area of a black hole was like what is called the entropy in thermodynamics. It would be a measure of how many states a black hole could have on the inside for the same appearance on the outside. But the area couldn't actually be the entropy, because as everyone thought they knew, black holes were completely black and couldn't be in equilibrium with thermal radiation. There was a golden age in which we solved most of the major problems in black hole theory. This was before there was any observational evidence for black holes. In fact, we were so successful with the classical general theory of relativity that I was at a bit of a loose end in 1973 after the publication with George Ellis of our book, The Large-Scale Structure of Spacetime. My work with Penrose had shown that general relativity broke down at singularities. So the obvious next step would be to combine general relativity, the theory of the very large, with quantum theory, the theory of the very small. I had no background in quantum theory, and the singularity problem seemed too difficult for a frontal assault at that time. So as a warm-up exercise, I considered how particles and fields governed by quantum theory would behave near a black hole. In particular, I wondered, can one have atoms, in which the nucleus is a tiny primordial black hole, formed in the early universe? To answer this, I studied how quantum fields or particles would scatter off a black hole. I was expecting that part of an incident wave would be absorbed, and the remainder scattered. But to my great surprise, I found there seemed to be emission from the black hole itself. At first, I thought this must be a mistake in my calculation. But what persuaded me that it was real was that the emission was exactly what was required to identify the area of the horizon with the entropy of a black hole. It is summed up in this simple formula, which expresses the entropy in terms of the area of the horizon. And the three fundamental constants of nature, c, the speed of light, g, Newton's constant of gravitation, and h bar, Planck's constant. I am proud to have discovered it. Later work uncovered a deep reason for this formula. General relativity can be combined with quantum theory in an elegant manner if one replaces ordinary time by imaginary time. This is called the Euclidean approach because it makes time become a fourth direction of space. The Euclidean space-time is smooth and contains no singularity at which the equations of physics could not be defined. It solved the fundamental problem that the singularity theorems of Penrose and myself had raised, that predictability would break down because of the singularity. The radiation from a black hole will carry away energy, so the black hole will lose mass and shrink. Eventually, it seems the black hole will evaporate completely and disappear. This raised a problem that struck at the heart of physics. My calculation showed that the radiation was exactly thermal and random, as it has to be, if the area of the horizon is to be the entropy of the black hole. So how could the radiation left over carry all the information about what made the black hole? But if information is lost, this is incompatible with quantum mechanics. This paradox had been argued for 30 years, without much progress, which is what often happens in research. But if you get stuck, it's no good getting furious. You just have to keep thinking about the problem while working on something else. Eventually, I found what I think is its resolution. Information is not lost in black holes, but it is not returned in a useful way. It is like burning an encyclopedia. Information is not lost, but it is very hard to read. In fact, Kip Thorne and I had a bet with John Preskill on the information paradox. I gave John a baseball encyclopedia. Maybe I should have just given him the ashes. The fact that I used to think that information was destroyed in black holes was my biggest blunder. Well, at least it was my biggest blunder in science. During the 1970s, I had been working mainly on black holes, but my interest in cosmology was renewed by the suggestions that the early universe had gone through a period of inflationary expansion, in which its size grew at an ever-increasing rate, like the way prices go up in the shops. In early 1982, I wrote a preprint proposing that the seeds for structures in our universe could be created by quantum effects during inflation. This was basically the same mechanism as radiation from a black hole horizon, except that this time it came from the cosmological horizon. I had used Euclidean methods earlier with Gary Gibbons to work out the temperature of De Sitter space. We held an field workshop in Cambridge that summer, attended by all the major players in the field. At this meeting, we established most of our present picture of inflation, including the all-important density fluctuations, which give rise to galaxy formation, and so to our existence. Several people contributed to the final answer. This was 10 years before fluctuations in the microwave sky were discovered by the Kobe satellite in 1993, so theory was way ahead of experiment. Cosmology became a precision science another 10 years later, in 2003, with the first results from the WMAP satellite. WMAP produced a wonderful map of the temperature of the cosmic microwave sky, a snapshot of the universe at about 1/100th of its present age. The irregularities you see are predicted by inflation, and they mean that some regions of the universe had a slightly higher density than others. The gravitational attraction of the extra density slows the expansion of that region, and can eventually cause it to collapse, to form galaxies and stars. So look carefully at the map of the microwave sky. It is a blueprint for all the structure in the universe. Superseding WMAP, today there is a Planck satellite, with the much higher resolution map of the universe you see here on stage. Planck will test our theories in earnest, and may even detect the imprint of gravitational waves predicted by inflation. This would be quantum gravity written across the sky. The original scenario for inflation was that the universe began with a Big Bang singularity. As the universe expanded, it was supposed somehow to get into an inflationary state, but I thought this was unsatisfactory. Unless one knew what came out of the initial singularity, one could not calculate how the universe would develop. Cosmology would not have any predictive power. What was needed was a space-time without singularity, like in the Euclidean version of a black hole. After the 1982 workshop in Cambridge, I spent time at the Institute of Theoretical Physics in Santa Barbara. I talked to Jim Hartle about how to apply the Euclidean approach to cosmology. According to this approach, the quantum wave function of the whole universe is given by a Feynman sum over a certain class of histories in imaginary time. Because imaginary time behaves like another direction in space, histories in imaginary time can be closed surfaces, like the surface of the Earth, with no beginning or end. Jim and I concluded that this was the only natural choice. We formulated the no-boundary proposal. The boundary condition of the universe is that it has no boundary. We had sidestepped the scientific and philosophical difficulty of time having a beginning by turning it into a direction in space. In this picture, the universe will be spontaneously created out of nothing. It will start out almost completely smooth, except for the tiny departures predicted by inflation, which then give rise to all the structure in the universe we see about us. Around the time of my no-boundary work, I decided to write a popular book. I thought I might make a modest amount to help support my children at school and the rising costs of my care, but the main reason was because I enjoyed it. While I was writing it, I visited CERN, and I became critically ill with pneumonia, and lost my voice due to a tracheotomy. But I kept putting a lot of effort into the book, because I think it's important for scientists to explain their work, particularly in cosmology. I never expected a brief history of time to do as well as it did. Not everyone may have finished it, or understood everything they read. But they at least got the idea that we live in a universe governed by rational laws that we can discover and understand. There are many ambitious experiments planned for the future. We will map the positions of billions of galaxies, and with the help of supercomputers like Cosmos, we will better understand our place in the universe. Perhaps one day, we will be able to use gravitational waves to look right back into the heart of the Big Bang. Most recent advances in cosmology have been achieved from space, where there are uninterrupted views of our vast and beautiful universe. But we must also continue to go into space for the future of humanity. I don't think we will survive another 1,000 years without escaping beyond our fragile planet. I therefore want to encourage public interest in space, and I've been getting my training in early. So let me finish by reflecting on the state of the universe. It has been a glorious time to be alive and doing research in theoretical physics. Our picture of the universe has changed a great deal in the last 50 years, and I'm happy if I have made a small contribution. The fact that we humans, who are ourselves mere collections of fundamental particles of nature, have been able to come this close to an understanding of the laws governing us and our universe is a great triumph. I want to share my excitement and enthusiasm about this quest. So remember to look up at the stars and not down at your feet. Try to make sense.
So at any rate, here's the picture of the observatory on the screen. I don't know if my pointer will go there. Do you see a pointer up there? Yay! I've got a pointer instead of a laser pointer. Anyway, what you see in the middle is this gigantic mirror. It's 26.5 meters across. Okay, if I use metric units tonight, for those of us in the English units, it's 21 feet. It's bigger than what you see there on the screen. Anyway, it is protected by a big umbrella, a sun shield we call it, which is as big as a tennis court. And is a joint project of NASA along with European and Canadian space agencies. It's an enormous project. It's the most difficult one we've tried at NASA in science and engineering for science. It's clearly not as difficult as the Apollo program, but all the same, it's just very appropriate that we should be naming it after James Webb, the man. So to start with some of the big questions that are in front of us, some of the people asked these things before we got started here. How did we get here? So we know quantum mechanics, we've known about it since 1925 or so. We know that it governs the properties of everything. But if you want to know how anything complicated works, you cannot solve the equations. You have to go build it and measure it. We know the universe started expanding, that it was very smooth and very hot when it was young. We know that it's unstable in a whole host of different ways and that energy can be released from reorganizing material into different shapes. So its complexity can build naturally. People didn't appreciate that, but it's a natural thing for complexity to grow here. The universe is probably infinite. I can't prove that to you. It is very old. It's about 13.8 billion years old, which means that there's been plenty of time and plenty of chances for the universe to do things that are very improbable, such as perhaps ourselves. There are not very many places like ours, so we might be the only ones, maybe not. But at any rate, each of us is quite unique. We know about stored information. We know how that works a little bit. We have evolution based on the stored information in our DNA. And when mistakes are made in the copying and the sorting, we get individuality. We get to blame our parents for all our troubles. And we also can say we have probably evolved, which I mark here as survival of the lucky. Because a long time ago when Darwin talked about evolution, people said, well, survival of the fittest. And since we're here, we concluded that we were the fittest. So that's not very good logic. We have evidence from the geneticists that perhaps our ancestral population very nearly perished, that they were down to a few hundred individuals. So we're here because those people were lucky. And we nevertheless claim credit. We have learned about, in engineering, feedback loops, and we are still trying to understand how that works. Just an example, I'm standing here and you still think I'm the same person even though almost all of my atoms have been replaced numerous times, except for my teeth and the chromosomes in my nerves. So the rest of it has been changed out and you still think I'm me. So there's a lot of mysteries besides astronomy to think about, and I just wanted to tell you there's a little bit more science to go. So astronomers look back in time. I guess everybody knows this one. I just like to draw this picture because it's my own hand-drawn picture. And so it shows you that you can look back in time by looking at things that are far away. And we know the speed of light is 1 light year per year, by definition. So we know how far back in time we're looking if we know how far away we're looking. So we survey the universe. We draw triangles, just like you were supposed to learn in high school. It's not that hard. If you know two angles and one side of a triangle, you can calculate the whole shape of the triangle. So that's surveying. The other method that we use is if we can't use the surveying method, we say, well, I'll look at those stars out there, and if I can convince you that those two candles that I drew in the picture are identical, and one of them just looks fainter, we say it's because it's farther away, and we can get the relative distances. So that's worked pretty well. It's hard work, but it's standard practice. The other thing we need to do is how fast are things moving toward us or away from us, and we use the color of light to measure this. If you spread out the light of the fireworks displays that you see in July the 4th, you see each of those colors comes from a particular chemical element. We can see them in the light of the sun, either as dark marks across the rainbow, if we make a good optical instrument, or sometimes they actually shine out. In a way, from this method, we can find out what's in the sun, how hot the sun is, how it moves, and in particular, we can tell if an object is coming toward us or away from us if the pattern of all those wavelengths is systematically shifted to longer or shorter wavelengths. So this is called the Doppler shift. We've known about it since the 19th century. So after a lot of preliminaries, Edwin Hubble became the first person to draw us a graph to show this effect about distant galaxies. So 1929, he measured or tabulated the accumulated information about how far away are galaxies and how fast are they going. And this is the picture he gave us. First graph to show that the distant galaxies are rushing away from us with a speed proportional to distance. Divide the distance by the speed, you get the age of the universe. Real simple. It's not such a great mystery, but it was found out in 1929, and so we forget it was so long ago, and we now think it's a big mystery. So he did get the wrong answer for the age. Measuring that distance is actually pretty hard. And the biggest problem that he had was the standard candles that he were using close by and far away were actually different kinds. So he didn't know that, but we took a long time to find that out. Now we know, and now we argue about the slope of that line within 1% or 2. So we made a lot of progress. So David mentioned in the introduction that we made a satellite to measure the Big Bang radiation. Here it is. This is called the Cosmic Background Explorer satellite, and it was made based on my failed thesis project and many other ideas to measure the heat of the Big Bang. So we measured it. It came out right. So I'm not going to skip over the details, but we'll just summarize it with a single chart telling you about the early universe. So we now know the early universe was very hot and very compressed. It probably has no center, at least we've not been able to find any sign of one, and there's no sign of an edge. You cannot see all the way to an edge because we haven't had an infinite amount of time. So even if light has been traveling all through time, you can still only see 13.8 billion light years at the speed of light. So we have the imagination says it's an infinite universe expanding into itself. There's no other universe out there for it to go into. And curiously enough, there is not a first moment. This confuses people a lot, but just imagine running the expansion movie backwards. So here we see all the galaxies are rushing apart. Imagine that they rush towards each other instead. When they start to collide and merge together, they get really hot. Atoms are destroyed, they're turned into individual particles, and you keep running backwards in your imagination, and it gets hotter and hotter and denser. But you never can get all the way to time zero. It's a curious thing. So you cannot actually say the universe was created. There was not a first moment in which it appeared. It has always been here. And this is just a curiosity of mathematics. But a lot of people called it the instant of creation. Well, it's not really. So it's also not a big firecracker because it's just the wrong picture. If you think of a firecracker, you think of a little thing happening at a place and a time. What we actually have in mind as astronomers is an infinite universe expanding into itself. So probably also there's no end, but I can't prove that to you. So that was the basic demonstration that the universe is as we claim. And we got a lot of evidence for it now. Now, what are we going to do about that? Well, even before the Great Hubble Telescope was launched, we started thinking about what are we going to do next after that. So one of my colleagues here, one of the future speakers in our series is Garth Illingworth, sitting here in the front row. And he and a lot of other people had a conference, and they said, what are we going to build after Hubble? So the book addressed the question of what do we not know, and why don't we know it, and could we answer it with a bigger and better telescope? Of course, the answer is yes. And they worked out a lot of the possibilities, including some of them that look a lot like what we actually ended up building. More conferences were held, and every 10 years the astronomers have this giant festival where we write a book about what's our top priority. In 1990, they didn't actually come out and say that they needed this new great telescope that we're building, but the committees, the subcommittees said so. So even in 1990, a long time ago, just a few months after the COBE satellite was launched, we already knew we had to plan for the future and something to come after Hubble. So here is the Hubble itself. Hubble is 27 years old, almost 28. Can you imagine that? It's going very well. It's been serviced, as you know, 5 times by astronauts that went up, visited it, put in new equipment, better equipment. This Hubble concept goes so far back in time that it's hard to imagine how primitive the equipment would have been if we were stuck with the old stuff. So we were really thrilled that you could do that and upgrade it so many times. 1990 was launched in April. So I guess everybody knows that we had a problem shortly after that. It was not in focus. So here's the astronauts working with the Hubble telescope. And here's a picture of a galaxy we took shortly after the launch. Bummer. NASA had a lot of jokes thrown at us. But we said, and Congress said, please fix it. And we did. So this was brilliant and wonderful, and immediately told us the universe is different from what we thought. So a committee was formed as soon as we had this to work on, and they said, what are we going to do next now? And they wrote a beautiful little book called HST, that's Hubble Space Telescope and Beyond. And they wrote an extraordinarily poetic little book that said, please build us a telescope that does infrared astronomy and make it bigger than before, if you could. So it still gives me chills to read that book because it's so well done. Committees don't always write good books. This one was. So here they are. Here is Alan Dressler, the chairman of that committee. And there's Dan Golden next to him. They met. Dan Golden heard what he had to say. And within a few months, at the meeting of the Astronomical Society, Dan Golden gave a plenary talk, and he said, I see Alan Dressler here. All he wants is a 4-meter optic that goes from a half micron to 20 microns. And I said to him, why do you ask for such a modest thing? Why not go after 6 or 7 meters? And he got a standing ovation. So I figured that was our first peer review, and it worked. Immediately after that, astronomers and engineers from everywhere wanted to work on this new project, and so we started. So we've had grand ambitions, and we are about to get there. So many more reports were written. So what was in that little book? Many mysteries that could become discoveries. What happened after the Big Bang? How did the first stars and the first black holes and the first galaxies grow? And what else could there be out there? How did the galaxies grow? Did the black holes start first and make the galaxies, or did the galaxies make the black holes? How do the supernovae and other exploding things affect everything? What's this dark matter and dark energy about? We were just beginning to understand about it. In fact, dark energy had only been guessed at. It wasn't really known yet in 1995. How do the stars form, and what happens when they get old? They blow up, some of them, not everyone. The sun is not going to blow up, by the way, but it will change. Exoplanets we just didn't know much about. We were just getting on to that. There were a few of them out there. Now we know that there's zillions, and that's a technical number. So pretty soon we were able to take a very long exposure with the Hubble Space Telescope called the Hubble Ultra Deep Field, and this picture shows a surprise. This is a picture of a place where there's like one star in this picture, and all the rest of those little dots are galaxies. And it's spectacular because it was a surprise. We knew before we flew the Hubble telescope that galaxies could not grow very quickly. We must be able to see them growing with the Hubble telescope. By looking far enough out in space and far enough back in time, we could be able to tell how that worked. Well, the picture here shows us, yeah, that's not true. There are a lot of little red specks on there that say, guess what? The first galaxies were too red to even get into the Hubble wavelength range. And they were too faint for Hubble, even if it could cover it. So please, NASA, please build us a bigger telescope that can pick up the infrared light. A few years later, we got to discover this effect. This effect is that galaxies that are supposed to be pulling each other together because of their mutual gravity, they're actually flying apart faster and faster all the time. This is now what we call the dark energy. The people who found this out got their Nobel Prize in 2011 because it was such an enormous surprise. They did it with that standard candle method, by the way. They said those little supernovae out there are 20% fainter than they should have been, so something's up. It was a little hard to convince people that they were right, but they were right. And now we have lots of confirming evidence. So now I've got a movie to show you, which is, from my perspective, the most beautiful movie I have ever seen. And now we need the lights down, because I'm going to show you I'm going to show you how the galaxies may have grown from the very first moments. So can we get the lights all the way off? Maybe not yet. Maybe they didn't hear. I need to show you the movie anyway. So here's the movie. It shows the effect of gravity pulling cosmic material back together. So the gravity acting on the little inhomogeneities, the little seeds in the Big Bang material, is able to stop the expansion. So the computer scientists have simulated this in a box of universe that they're rotating in front of your eyes so you can see the structure growing. And within a billion years of the whatever started it going, the structure has already appeared. Galaxies are forming. They are forming in huge strings of material. They are stretched out in a very non-random fashion. These huge strings are actually coming together in sheets. Once in a while, the computer has lined up the line of sight so that it looks like everything is all in one plane, like right there. So who'd have thought that? Astronomers were stunned when they found this is actually what we see in the sky as well. So this movie shows something you could never observe because it shows time dependence. And we're not going to be able to wait for billions of years to see if this picture is correct. But what we can do is take pictures with the Hubble and with the James Webb Telescope and see if the pictures match up with what this movie predicts. This is not the most current movie, but it is the most beautiful one that I've seen. So here the movie is showing the universe has gotten to be about 7 billion years. When the universe is 9 billion years old, that's when a lot of these explosions that you see start to slow down. And that's a good thing because that's also when the solar system is being born. And it would be really hard to start a solar system next to an explosion like that. So just about this point in the movie, that's when our solar system turns up and the great explosions slow down. Those explosions are coming from black holes and from exploding stars. So is this movie true? Got to take a picture, got to take a lot of pictures, and reason through the evidence. And eventually we'll be able to tell you what's the matter with this movie and does it turn out right in the end. But it's pretty darn good. By the way, it took modern technology to even be able to make the movie. Because I think what we have coming here next is the list of people who made it. And they needed millions and millions of CPU hours and the best computers you can possibly find. So we couldn't have done that a few years back. In fact, why do we need big computers like that? Well, other government agencies need them, and so do you. So anyway, what else have we seen? Here's a beautiful picture taken with the Hubble. Shows a nearby galaxy called the Whirlpool Nebula. And in the lower right corner, I've got a picture that was drawn by Lord Rosse in 1845. He had the biggest telescope in the world in that year. It was made with a big metal mirror about 6 feet across, 2 meters. And he saw the same features that we see today, and he was remarkably successful at that. Here's another beautiful picture from Hubble. This is taken not only with the Hubble, but also the Chandra Observatory. This is the exploded star called the Crab Nebula. We now know that it blew up on July the 4th of AD 1054. So that's part of the story of where our atoms come from. A lot of the chemical elements of life were produced in that star that blew up and released for recycling. So you all are recycled from this stuff. It's all right. We're breathing dinosaur breath too. So now we get to the telescope of my great joy. This is the James Webb Space Telescope. As I mentioned, it is named after James Webb the man, not the current politician, but James Webb who went to Jack Kennedy with the plan. So it is a project, a joint project of NASA with the European Space Agency and the Canadian Space Agency. There is the big mirror in the middle. It's huge, and it is so huge that it has to be folded up for launch. The telescope will be cooled down to about 45 degrees above absolute zero, so that it doesn't emit very much infrared light. And we are planning to put it up in 2019 on top of a European rocket called the Ariane 5. Here's a little bit about the telescope design. For you telescope builders, it starts off with a Cassegrain telescope, but improved by having a third mirror that you can't see in the picture. Excuse me. And this is a telescope made out of 18 pieces. The big primary mirror has 18 segments, all made out of beryllium, coated with gold and polished to the basic perfection that they need when they will be cold at the operating temperature in space. The mirrors are about 2 millimeters thick, and getting to be perfect at the cold temperature is a huge challenge. In fact, when we said we were going to do that, people laughed at me for many years, but we did it. We have a package of 4 different kinds of instrumentation inside: cameras and spectrometers. So we're going to take pictures of pieces of sky, and we're going to stretch out the light of different objects into the colors so we can analyze what's inside and how they're moving. So this is for the technical folks. It covers all the wavelengths from 0.6 microns, which you could see. It's more or less the color of a red laser beam, out to 28 microns wavelength, which you certainly cannot, but your friendly rattlesnake would be able to pick it up if it were bright. So very powerful. So whatever astronomy that you would like to do, you think about using this equipment, we can probably do it for you if it covers that wavelength range. By the way, the astronomers in our world are now writing proposals to how to use this telescope, and they're due in April. So pretty soon we'll be able to tell you the basic plan of everything we're going to do, or most of the things we're going to do in the first year of operations. So now I want to show you roughly what happens to the telescope hardware. So here's the roadmap to get the telescope up. We start by putting the telescope together in our clean room out at Goddard. A few of you may have seen it in our clean room. Then we shook it and tried to see how close it was to breaking before we launch it, and it passed all that. This little picture shows you the telescope in a clean tent on top of a vibrator, gigantic vibrator. To shake it and see that it'll pass the test. We put it in a giant mailbox, send it around the Beltway to the Andrews Air Force Base, put it in the telescope in its truck, with its truck, into the giant C-5C aircraft, flew it to Houston, unloaded it there, put it into the vacuum tank there. I'll show you more. We put it back in the airplane, and we've just flown it out to California, to where the Northrop Grumman Company has their facilities. And it is about to go through the next stage where we merge it with the warm part and we continue testing it, make sure it unfolds and folds up again. Then we put it in a slightly expanded version of the mailbox, put it on a boat, send it through the Panama Canal, send it to French Guiana in South America, put it on the rocket, push the button, goes up into space, goes way out there, about 1.5 million kilometers, English units, 1 million miles. And it unfolds out there and does its work. So that's its trajectory. It's not quite all the way there, but about 1.5 years of work left. So here is a movie taken of the telescope in its clean room at Goddard Space Flight Center. It shows the robot putting the telescope mirrors on. Here we have the telescope in its plastic tent. We have put it on top of the shaker so to see if it will survive launch. Here we're putting it into the mailbox, shipping container, pushing it out through the door, and getting it ready to go into the vacuum tank in Texas. And that's the door of the vacuum tank in Texas. Here's the truck driving down the highway very slowly. There it is. You can see it's a snug fit in the aircraft. There's about 1 inch clearance around the mailbox inside the airplane. Landing in Houston, the truck drives out. Here it comes. Have to move the traffic lights in a few places to get under them. This just gives you a little hint of the civil engineering that it takes to move something this massive and this important around the world. So there's the door of the big vacuum tank in Texas, which, by the way, was originally built for the Apollo program. That's where the astronauts practiced walking down their ladder onto the surface of the moon. So in that tank, we have put our telescope and we tested it there. We focused it, made sure the mirrors would move, made sure that we would not encounter the Hubble focus problem. So we tested it end to end, shine light all the way from the beginning to the end of the telescope. It spent 3 months in there and it came out and we were happy. It's a very good telescope. So then we take it out. There's the door. And it comes out onto a very short railroad track. And we will put it back on the airplane. There's the railroad track. I think that's that one, that movie. There it is, looking big and beautiful. Gold. Why gold? By the way, it's because it's the best reflector for infrared light. Why is the mirror material underneath beryllium? Because it's the lightest and the stiffest, and it keeps its shape when it's cold. So now we have shipped it out to California, and it is going to meet up with this part, which we have completed almost at the Northrop facility. Here is 1.25 years worth of hard work condensed into a few minutes in their gigantic clean room. Bring in the parts. Here's the big clean room. Lots and lots of people. We're just beginning to put together the spacecraft bus, which is the framework that holds up all the avionics, the transmitters, the receivers, the computers, the power supplies, rocket fuel tanks, all those things in the middle. You can see it takes a lot of people a long time to do this. So when I talk about the engineering miracles that it takes to enable scientific discoveries, it's not just engineering, it's a lot of people with their hands on the hardware for a long time. Here you see that we're beginning to assemble the framework that holds up the sun shield, and that was a simulation that they just put on the top of the telescope framework itself. You see people up on these very high lifting devices looking down and assembling things. This is an extraordinary process. You see people are strapped to their diving board so they can't fall off and they can't drop any tools. Here we are preparing to put together the sun shield, which is 5 layers of very thin plastic covered with a metallic coating so it can reflect the heat of the sun away. Say, golly, geez, isn't that pretty hard? And the answer is yes, it is. As far as we know, there's no other way to get the science that we're after. So it makes you tired just to look at it. And our people have been there working 6 or 7 days a week for a long time to make this happen. Here you see some of the sun shield layers have been lifted up so we can get at them. They have to be very carefully folded up. And of course we have to make sure that they unfold properly. You can't really test it in 0 gravity in a vacuum. So what you have to do is pretend as well as you can here on the ground with things that hold up the weight of the equipment so you can tell. So this is an example of what it takes to build a really big telescope in space. Lots of people, lots of hardware, lots of equipment that you never thought you would need to be able to get at it. Support equipment. So after we finish all of this, we will then take this hardware and put it on a shaker, make sure that it survives the launch. We'll put it in a vacuum tank and make sure that it behaves itself in a vacuum. And we will rehearse more than once, folding it and unfolding it. So golly gee, that's hard. And that's why I say this is not a scientist's job. It takes an enormous effort by a team, has to be well organized, and it is possible. Not easy, but it is possible. Here they're finishing putting together the sun shield with its 5 layers of plastic, each as big as a tennis court. Now we're going to pull on the cables and tighten up those sheets of plastic so they have the right shape. This is what it will look like when it's in outer space. except you won't be able to see it because this side is going to be in the dark. This is the thing that makes the telescope always in the dark. So that's the engineering miracle that's currently going on at Northrop Grumman, and we will come back to what we're going to do with it. So here's where we're sending it. We're sending it 1 million miles, 1.5 million kilometers out in space to Lagrange point 2, which is over here. Sun, the Earth, a little farther than the Moon. This is definitely not to scale. Oops, didn't mean to do that, but here is the movie of the unfolding. It looks simpler than it is in the movie, and it goes quicker than it does, because we actually have 2 weeks to make sure this movie works right. And you say, well, how do you know what you're going to do if it doesn't work right? We have multiple ways to make everything happen. We've got 2 of everything where it's possible, and we have sensors to tell us whether things have worked properly. So there it is, unfolding itself in outer space without human touch, but with lots of human attention. We're watching it from here with our equipment. So when we hired the company to do this, they said this was not the most complicated thing they'd ever done in space. But I think it's right up there in the top few. So there it is. It still isn't in focus yet. It isn't even set up yet. We have to wait for it to cool down to the right temperature, turn on the cameras, take the pictures, and run everything that we have already rehearsed to get it to focus up. But we know it can. There it is. After a few weeks in outer space, it'll be like this. So just a few little words about what we're going to do with it. The sensitivity is extraordinary. If you were a bumblebee at the distance of the Moon, we'd be able to see you. And astronomers call it nanojanskys. It's a very small unit of brightness. We'd be able to see you both with reflected sunlight and the heat that you would emit if you were a bumblebee out there. Now, some things are a lot brighter than a bumblebee, and we'll be able to look at all the planets, including Mars and outwards. But we do have to kind of squint for Mars because it's so darn bright. So whatever you want to know about the solar system, from Mars outwards, we'll work on it. We're going to take pictures like this, only different. This is one of our most beautiful NASA pictures taken with Hubble. It's a place where stars have just been born and are being born today. And golly, isn't it beautiful? And golly, you can't see inside that cloud. So wouldn't we like to see inside the cloud? So yes, you can if you use infrared light. Hubble has some infrared capabilities, so that's what you see with the Hubble and its infrared camera. You can see partway into the cloud. And you can also see there were a lot of stars hiding behind that beautiful cloud. So this opens up a new territory for astronomers. It's not just for cosmology. We're looking farther out into space and farther back in time, but also to see how are stars like the Sun being born today. We will be looking at things in the outer solar system. Here's a place that's of great interest to many people, including some of our favorite congressmen. Europa. It was a satellite of Jupiter that was discovered by Galileo. And this picture was taken by a mission that we called Galileo. And it shows that Europa has an ocean covered with ice. And recently we found that there's pictures of water spritzing out from this beautiful little satellite. And so people say, wouldn't this be a great place to look for life? Got an ocean, got places you don't even have to drill in. You just go land or even fly through the plume coming out of the geysers and see what's in it. You have a chance to find out if there's organic material. I think it takes a little more work to see if there are bacteria, but this is clearly a top priority for scientists, and we're glad that some congressmen like it. We will certainly be looking farther out also. We know that there's at least one very powerful way to study planets as small as Earth. When they go in front of their own star, they make the star blink a little while, and you can figure this out. Some of the starlight goes through the atmosphere of the planet on its way to our telescope, and we can analyze that part, spread it out into the spectrum and the rainbow, and get the chemistry and the temperature and the properties of that atmosphere. We've already practiced with some planets that we've seen that are big and bright enough that Hubble can do this trick, and even the small Spitzer Space Telescope can do it. So we're working on that. We are sure we're going to try this some more with the Webb telescope. we will be looking for things like the TRAPPIST system. You probably heard about this one. This is a system with, let's see, 7 planets, not so different from the size of Earth, and they are in orbit around a rather small star, about as big as our planet Jupiter. But these are all close enough to the temperature of Earth to be interesting. The 3 in the middle are quite possibly capable of having liquid water on the surface. So we certainly don't know that they do, but obviously an interesting place to go looking. So, oh, come on, I didn't want to show it twice. Okay, next picture, please. Just a few more speculations before we wrap up. Everybody wants to know, are we alone? And the answer is we don't know, but we're going to work on it. So the big question next that we can work on is, well, how special is Earth? We know Earth is special within the solar system. It's the only one that has these special properties. It's got oceans and continents. It's got a big magnetic field. It's got a big moon. It's about the right temperature. It has plate tectonics to recycle the ocean and the rock. It's about the right distance from a nice star. The star lasts a long time. So that's pretty interesting. So we want to compare what we have in our solar system with what's way out there. So how are we going to know about that? We need to build another telescope. How did you guess? So we have many sketches of bigger and better telescopes to follow after this one. But one of them, at any rate, is called the Large UV Optical Infrared Telescope. It may be 2 or 3 times as big as the Webb telescope and capable of seeing little planets as little dots orbiting their own stars, in which case you could find out a lot more. So we'll wrap up here. I think we have some time for questions. But I just want to say we are still not going to have the galactic civilization that Isaac Asimov wrote about. We cannot travel to the nearest stars in person. We have not discovered warp drive. I don't think there are any very good hints out there yet. So I'm sorry about that. But if we make robots and the robots are interested and patient, they can go. They don't have to breathe on the way like we do. So we astronomers, on the other hand, we travel at the speed of light. We receive signals from far away, and instantly we know what's out there. We have to think about it. We have to interpret our fuzzy little dots, but we can find out. So I promise you will not be disappointed. Thanks. So what's the plan for microphones for our questions?
Well, I can field questions. John will repeat the questions if that's okay.
Sure. Yeah.
Okay.
So we take questions.
Right here, we'll start.
On the James Webb Telescope, the panels that you have there, you said they're plastic. Well, they seem to be a lot more fragile than anything that's on the Hubble. So what do you do about micrometeors and meteor?
So her question is about the giant sun shield. The gigantic umbrella is actually made of very thin plastic. It's about not much thicker than your laundry bag. So it is fragile, but it's tough. So micrometeorites will make holes in it, and we don't care. We know how many there are. We know how big the holes will be, and it doesn't matter. There will be little pits all over the mirrors, and we also don't care. There are not very many of them, and they're not very deep. So it's all right.
As you know, we're in overflow, and I'll take a few more questions, but then we will turn it over to the overflow people to ask questions. Question there.
What are the lifespans of both the Hubble and the Webb?
Okay, the lifespans. The Hubble's already 27 years old, almost 28, and it's not wearing out. So 5-10 years more is quite possible. And it's still doing great science, so I don't think anybody would turn it off if it's still working. Eventually we have to do something because we can't let it fall on Moscow. Oh, and the Webb telescope, our planned life is at least 10 years.
Yeah. Okay, in the white.
Are you expecting to go after transient events, supernovas, gravity wave events? How are you expecting?
So his question is, can we go after transient events like gravity events and supernovae? Answer is yes, but we're not that quick to respond. You have to phone us up with your urgent request, and then we have to say, okay, we'll think about it, and then we have to make a plan, and then we have to talk to the spacecraft. So it takes a day or two to do that. So please plan your urgent activity in advance.
Okay, one more here, and then we'll go to the planetarium.
Oh, where do we put it relative to the Earth? It's a 1.5 million kilometers out farther from the sun than we are. So it moves around the sun with us all year long and stays out there. So it's overhead at midnight, 1.5 million kilometers out.
Okay, any questions from the planetarium?
Since the space shuttle doesn't go there anymore. Is this not working?
I'm not sure.
Okay, so space shuttle doesn't go now. What do we do in case of servicing? We actually have no plan for servicing. There's only one thing that would be relatively easy, which is to put more gas in the gas tank. And we have made a plan where we would be able to dock a servicing module with it, but we're not planning to do it.
One more from the planetarium.
Yes, 1.5 million mile journey, spring launch in 2019. How long before you will have this thing sending back pictures?
Oh, so how long before we get pictures? It takes a total of about 2 weeks to get it unfolded, a total of 6 months to get it all set up and working. And then you should expect beautiful pictures. Okay, so we get our communications back to Earth by way of the Deep Space Network. So there's some big dishes out in the Mojave Desert, and some also backup ones in Australia that we use. So big dish. Oh, so why do we build more than one kind, really? In the Atacama Desert and other places in Chile, we have special things we could never do in space. Number one, you can make them a heck of a lot bigger on the ground, and so that always wins if you can. But you can't do it at all wavelengths. So each different thing that you want to see shines best at a certain different wavelength. So the hotter the thing is, the shorter the wavelength you need to use. So some wavelengths come through the atmosphere of the Earth, and some don't. So we basically, that's what sets what kind of telescope you need to study what. The wavelength in question, which comes from the temperature of the object.
Okay. Another one from here, and then we'll move to the planetarium again.
What project are you most excited about for the first year?
Oh, for the first year, I haven't actually got a favorite project yet. We have hundreds of things we're going to look at that we already know. And I think my favorite one will be the one that tells me something I don't know anything about yet. The one that is a big surprise. So you can say what you're going to look at. You can't say what you're going to see. That's the cool thing about it.
Planetarium, any questions?
What was the single biggest or hardest engineering challenge in making the telescope?
Oh, the single biggest challenge is definitely the mirrors. Those big mirrors, they are so light that you could easily lift one of those 18 segments yourself. We won't let you. But you could, because the metal has been cut down to 2 millimeters thick. And nevertheless, it's polished to the same accuracy almost as the Hubble telescope has.
Wasn't there a problem with beryllium, that it would crystallize?
So beryllium's an interesting material. Beryllium comes in nature as hexagonal crystals. Well, that's not good. It's not going to keep its shape when it cools down. So metallurgists have spent a fortune and a long time making beryllium into a perfect material. Make powder, compress it into a vacuum in a furnace, and make a block that's totally uniform. And it doesn't warp when it cools down. So that's amazing.
Remarkable. In the blue.
For the Hubble Deep Field, they had to point the telescope away from stars and find a black patch in the sky. If you were to configure for a James Webb Deep Field, what would be the criteria you might use?
So the question is, why do we, is about the deep fields. Towards the Hubble Deep Field, where there's nothing there to look at but one star or so. We have basically already chosen those deep fields. The ones that are most useful now are the ones we already looked at, because we already understand them greatly. So now we know those are exciting places to look. So the Chandra Observatory has looked in some, the Hubble has looked in some, Spitzer has looked in some deep fields, and all those are really interesting. So they're all being proposed.
The planetarium again. Anybody?
If you could add anything to the telescope, what would you add?
Oh golly, if I would love to be able to put a remote occulter out there, but I can't. A remote occulter is a thing that can cast a shadow of a distant star on the telescope so that you can look for planets next to it. So we'd love to do that, but it's not feasible this time. Maybe next time.
Wouldn't you like to put an observing chair there?
An observing chair, nah, I don't really want to go there. I need to breathe.
Oh, details. Planetarium, one more question, then we'll come back here.
How was the decision made to launch the satellite that launched the telescope on an Ariane 5?
Oh, how was the decision made to launch on an Ariane 5? It was actually a long process. The Europeans offered this as a part of their contribution to the partnership. And then it took us a long time to say, yes, that's the right answer.
Question here and then there.
What is the source of power for the James Webb Telescope? Is it RTG or is it all solar or what?
So his question is, what's the source of power? And we use solar cells for the whole thing. We have a battery that's good for about an hour because we fly through the shadow for a little while. And after that, it's always sunshine on one side, always dark on the other. Do we offer additional information about dark matter and dark energy? Yes. I don't know what the surprise will be, but yes. We will certainly look for the effects of the dark matter because it has gravity and it changes everything. And we are going to pursue the same method that was used to discover the dark energy with the standard candles and all that. We can do it a lot better with a new telescope.
What's the biggest engineering challenge in keeping view of cold enough to make the observations, but also view the sun that you get found?
What's the biggest engineering challenge to keep the telescope cold and still have the solar power? Well, it's actually all solved with this gigantic piece of plastic. But that's not simple. You can't get a roll of plastic from the grocery store that does the job. So we have to stitch it together out of pieces, and it's a hard job. It's cost us a fortune to get that piece of plastic.
There was one up here. Yes.
What's the outlook for your 2020 budget?
Oh, the outlook for the 2020 budget, I have a crystal ball right here. But what we generally do is we plan for a level budget. We think Congress has been pretty darn steady with the budget they allocate to astronomy and all sciences as a fraction of NASA. And despite all the troubles that we have with the overall budget, we've been as level as you could hope to be for a long time. So steady support is what we plan for and hope to get.
Thank you. I have to break in now to say this concludes the live broadcast of the television viewing. Thank you for watching.